And our next presenter is Todd Kincaid, Ph.D. Dr. Kincaid is a groundwater scientist, underwater explorer, and advocate for science-based conservation of water resources and aquatic environments. He has spent the last 20+ years studying groundwater flow, contaminants therein, and the advanced rate of saltwater intrusion due to both overdrawing of the aquifer as well as sea level rise. He continues to advocate for advanced restoration and protection efforts with scientific, conservation, and government entities. Dr. Kincaid.
All right, thank you. Well, I appreciate the opportunity to talk to everybody today. It's always an honor to talk to groups like yours of passionate people. I very much enjoy sharing stories about the work that I've been able to do. So what I'd like to do today is just take you on a bit of a journey, what I think of as a journey of discovery about how springs work. So I'd start with just a little bit of a personal side and ask some rhetorical questions, because I know nobody can throw out answers here, but ask the question, have you ever swam against the flow of a strong Florida spring? And I'm guessing that many of you in the audience have. For me, my first time was at Wakulla Springs in about 1973. Later on, Wakulla Springs became my favorite place on earth, largely because I grew up in Orlando. I did get a chance to swim and dive at Blue Springs, but it wasn't quite in my backyard the way Wakulla was. I was one of those kids that you probably still see lined up along the edge of what I still believe must surely be one of the greatest wonders of the world. And that, of course, is springs. The question that I couldn't help but ask, and I think many people ask the same one, is that where does the water come from? You can't help but wonder that when you're holding yourself against the flow, struggling to get just a little bit further in. I remember stories of divers using anchors to pull themselves deeper into Blue Springs, past a constriction that used to be at about 120 feet deep. I also remember that some of those people died trying to get in those holes. There were and still are, I'm sure, loads of wonderful and crazy ideas about where the water comes from. I remember stories about people thinking that the water came from the Appalachian Mountains or from the Great Lakes, or even from a deep Great Lake that Florida floats on top of. Overall, the idea, I think, resonates that springs must come from a pure and ancient source of water that's impervious to harm. Of course, we now know that's not the case. That question, where does the water come from, really sparked my career, and I still chase answers to that question today. So in the presentation, I want to talk about what I learned about where the water comes from in school, what I've learned since I left school, how have springs and caves come to be. I'll just throw out this right now, is that you can't really talk about springs in Florida without also talking about caves. So I'm going to be talking about both, why springs are important, and what needs to be done to protect them. Of course, that's my perspective. Overall, I hope to be able to share with you my perspective on where the water comes from. So what I was taught in school. Okay, so this is a few slides to cover about 4 years of education. I can sum it up with one phrase that I still hear all too often, which is that there are no such things as underground rivers. As a groundwater scientist, we learned that groundwater flows through the spaces between the rock grains, between the little holes in between the grains of rock. Groundwater flow is a diffuse process and a slow process. Velocities tend to be on the order of feet per year or less, as what we were taught in school. The mathematical concepts that we use every day to solve problems about groundwater stem from people's research and study of the great sandstone aquifer underlying the Midwest of the United States, the Ogallala Aquifer. And those studies demonstrated that we could describe groundwater movement, aquifer storage, and contaminant movement, and be relatively accurate in our predictions. And as a consequence of that, which most of that started in about the 1930s, we took those techniques and applied them to every environment across the United States, Florida, of course, one of them. And then as I moved forward, I also learned that only amateurs study springs, whereas professionals study wells. And finally, I learned that there's no such thing as caves in Florida. And if they are, they're not significant. And even if they're there, they're too hard to deal with anyway. I remember my professor when I was a hydrogeology student at the University of Florida used to invite people to come and give presentations in our class. And one of those people was a man named Wes Stiles, who spent his career mapping and exploring and making films about the underwater caves of Florida. And later, another professional came from one of the water management districts and told the class that there was no such thing as caves. And one of my fellow students was brave enough to ask about Wes's videos. And at that time, he said that Wes surely must have staged all of those things in Hollywood, and we shouldn't be fooled by those videotapes. For me, I wasn't brave enough at the time to speak up and show that I was at that time diving at least 4 nights a week in the caves, exploring and chasing them as far as I could get. So just a quick little, keep on going, like how does this work? If we're operating in this porous media environment, the idea is that water flows diffusively between the sand grains and converges on rivers. And when it does this, you really can't have any springs if this is the case. So these little dots on the springs here wouldn't exist. Instead, you just have seepage pouring into the river and getting a river gaining flow as you went downstream. We also learned that there are 3 types of permeability, let's call it, or permeability framework of a rock or an aquifer. There's the porous media, which is the one on which all our mathematical concepts are based. There's fractured rock aquifers, which are very characteristic of the Appalachian Mountains or the northeastern part of the United States. And then there's karst aquifers. And for the longest time, people regarded karst as only being present in places like the Appalachians, where you could walk into caves or be able to explore places like Mammoth Cave. And certainly they weren't present in Florida. And just thought that one of the key concepts I learned that I still try to convey to people every day is a concept of the water budget or the hydrologic cycle. Water is neither created nor destroyed. It's always in constant motion. And so essentially, we are, as hydrogeologists, we're studying its pathway from the atmosphere through the ground and then out to discharge. So basically what you're seeing here is our hydrologic equation, which is that discharge, springs, discharge from the aquifer equals precipitation minus runoff minus evapotranspiration plus a change in storage. So change in storage means whether groundwater levels are going up and down. So essentially what that represents is the first principles of science, which is mass balance. I like to tell my daughter there's no such thing as magic. And this is an example of it. And by that, what I mean, and why I always come back to this is that pollutants don't just go away. A very common belief, at least when I started out, was that we put things on the ground and the ground absorbs them and they just go away. And that's not the case. They can be held in the ground for a long period of time, but quite often they travel into the groundwater and then out to the discharge. And then also, water that's pumped out of the ground doesn't come from a magic source either. It, of course, is captured from its pathway towards some natural point of discharge. And of course, in Florida, that's the springs. What I've come later to learn is really focused on the karst component. And so this is a map of Florida, obviously. And here in the darker colors, we have what is called the confined portion of the Florida aquifer, which is essentially where the aquifer is covered up by less pervious, less permeable materials like clays, specifically in Florida, as a clay unit called the Hawthorne Formation. And then what that does is it inhibits the ability of water and therefore contaminants to migrate vertically into the Floridan. The lighter medium color there is a thinly confined zone. That's where most of you are probably sitting right now, where there's some cover to the Floridan, but either it's thin or in some places breached, and therefore you can allow for rapid recharge and for rapid contamination in those places. And then finally, the lightest colored areas are the unconfined portion of the aquifer, where the aquifer material is literally sitting at or very close to the land surface. So what I want you to look at here is the black dots, which are what we call first magnitude springs. And the real cool thing about Florida, this place that you live, is that it has the highest concentration of very large springs of anywhere in the world. All the big spring systems that exist in Florida are discharged from big and diveable cave systems. And all but a few of these springs are unfortunately now impacted from nutrient loading. And if we were to go down the string and use our imagination in terms of the definition of a cave, I would argue that every single one of these springs is connected to some form of a cave system. Maybe not one big enough to allow divers to explore, but a cave system nonetheless. Now that I live in the western part of the United States, where water is a little bit more scarce, as Mark Twain said, whiskey is for drinking and water is for fighting out here. The springs that most Floridians would ignore, so the third and fourth magnitude springs, still springs that discharge more than 100 gallons per minute, would be places that people out here would kill for. And if we consider all of those springs, the number of springs in Florida jumps to the thousands. So there are just an enormous amount of springs distributed out through Florida. And finally, as I said, all of these springs are connected to caves. Florida has the longest underwater cave in North America. The longest caves in Florida are thousands of meters or miles long. The Wakulla cave system has more than 30 miles of mapped passages. And since we've been studying these things, we've been using tracers to try to map exactly where the water flows and how fast it goes through the aquifer. And we've learned that not only is groundwater not necessarily a very slow moving phenomenon, but it can move very fast, hundreds to thousands of meters per day. The longest trace that I know of in Florida was one that I was lucky enough to be a part of, where we put dye into a sinkhole and it came out about 18 miles away, and it took about 4.5 days to get there. So I'm going to jump up to Wakulla Springs. Hopefully most of you know where that is. It's in the Big Bend area of Florida. It's about 16 miles south of Tallahassee. So this is the city of Tallahassee up here. And Wakulla Springs is located here. This is a picture of it. One of the biggest springs in Florida as measured by discharge. If you look it up in the book, it discharge ranges from about 80 million to 1 billion gallons per day, which is between 300 and 3,800 Olympic swimming pools of water every day. The cave entrance is the largest I know of any spring in the world, actually, about 40 meters high, so about 100 to 120 feet high and about 200 or 250 feet wide. So it's a really big place. And it we used to regard it, or still regard it, as the Mount Everest of cave diving. So as a cave diver, all of our attention was focused on this part of the state for a very long time, dreaming about what it would be like to get in and explore the Wakulla cave system. Unfortunately, by the 1990s, Wakulla had become pretty heavily impacted from hydrilla and from algae, and it's an ecological decline. And we knew that to be the case from nutrient loading. But the question would be, where does these nutrients come from? At the time, when we looked at this, just like the pie charts that Aaron showed earlier, we could see that really the largest source of nutrient in the basin was the city's wastewater spray field. But that was located about 12 miles away. And since the common conception was that groundwater flows very, very slowly, it was literally thought to be impossible for that to be a source of contamination to the springs. So one of the first things that I did after getting out of school was to come back and organize a collaboration between divers and scientists. And we focused our attention on trying to answer big questions about Wakulla Springs. Where does the water come from? And most importantly, where does the contaminants that were causing this ecological decline come from? Over the years, we put together collaborations, and we did, the divers gave scientists previously unimagined access to the cave system. We installed meters, and we made maps, and we did dye traces, and created maps and models of the cave systems to use to try to not only educate people, but also try to collect the kinds of data we would need to answer these questions. Over the years, by let's say 2003, 2004, Wakulla became the world's most instrumented cave. We still have 7 hydrologic meters operating in Wakulla, collecting data at about 15-minute intervals that are measuring the temperature and the conductivity of the water, allowing us to understand how the water is mixing from different sources. And this map here, we're showing a map of the explored passages in Wakulla at about 2003. And from this, we were able to see and change people's perspectives about springs, and that the spring is not just a single source or a source of water from a single location, but in fact, water was mixing from multiple locations. We could tell that water from this B tunnel that extends up to the north was of one type of quality. Actually, the majority of nutrients were coming in from that tunnel. This D tunnel, a different water quality. And then weirdly, the vast majority of the cave passages headed south towards the coast. And these carried higher conductivity water, so higher salinities, and also where the characteristic dark water was coming from, where the spring would change from clear to dark during rainy seasons. After the instrumentation, we finally started to propose and were able to get budgets to do dye tracing. And then in this case, we put in dye, and what I'm showing are places where the streams go underground. And as a consequence, once the streams disappear, the idea is where does that water go? And we put dye in all these little red dot locations, building our understanding of velocities and flow paths and capabilities. And then ultimately, we wanted to answer this question about where does the water from the spray field go? So we started in 2002 at Fisher Creek, 1.7 miles in 1.7 days. 2003 at Black Creek, 2,670 feet per day. 2004 from Emerald Sink goes to Wakulla Springs, 7,650 feet per day. Finally, we traced from Ames Sink to get an idea of where over half of the city's stormwater runoff goes. It turns out it goes to Indian Springs, about 2,000 feet per day. They didn't believe us the first time, so we did it again. Comes out at about 1,600 feet per day, same location. Indian Springs, we then traced to Wakulla at about a mile per day or a little less. And then finally, we did the spray field, and it comes out that indeed it travels those 12 miles to the springs, and it gets there at a velocity of about 980 feet per day, or about 56 days. Same thing from a disappearing stream out the spray field property. And then finally, we wanted to see some interaction with the coast and realized that depending on the time of year, the water was flowing from Lost Creek to Spring Creek at the coast. And then in some cases, all of that water would turn around and flow back to Wakulla Springs, giving you the reason for the salinity changes in the springs. So in the end, we were very inspired by being able to make a difference, being able to work with the city and be able to demonstrate, use this scientific data here to definitively prove that the city was a contributing source of nutrients to the spring. And as a consequence, they invested about $200 million. I don't know, that number kind of has moved, but I think it's about $200 million in the construction of an advanced wastewater treatment system that dramatically reduced the spring. So what I like to say is that education plus science, and of course the little press doesn't help anything, doesn't hurt anything. You can make some major changes in your situation. And so the nutrient load at the spray field went from about 1 milligram per liter down to about less than 0.3 milligrams per liter as a consequence of that improvement. So then as we move out from Wakulla, I used to have to deal with the question of, well, maybe all these fancy caves and fast moving velocities or fast moving groundwater is isolated only to Wakulla Springs. And of course, that's not the case, but we still nonetheless had to go ahead and show it. This is a map that relates tracer test results to groundwater modeling predictions for Silver Springs, so Wakulla, just a little ways north of where you're at. And in this case, what I want to show is like this light blue zone. The model predicted travel time there is 100 years. So in this case, the model predicted 100 years, and the tracer test from there traveled to the springs in between 24 days and on the slow side, just over a year. And the lighter on the next zone, the model predicted travel time is 10 years. Tracer tests from locations in that zone showed that the travel time was in actuality between 50 days and just under a year. And then finally, in the closest zone, the model predicted travel time is 2 years, and the tracer test showed that it got there in 5 days, or even the slowest ones less than a year. So we see that there's this big sharp difference between how we're conceiving of the aquifer when we talk about management and protection, and how the aquifer actually works. And then even then, I still would go and give talks similar to this at different places. And I remember at a county that I won't pick on directly, but they gave me the phrase that there's no karst in my county. And I thought, oh, that's really interesting that this physical process should be selective based on political borders. But as a way of combating that, I throw out this example, which says from South Florida, from Miami-Dade, even a place where there are no big springs, no evidence of caves as we think of them at all, dye tracing proved that caves do in fact exist and groundwater flows very fast. You can look this up. I challenge you to Google the pink underwear test, and you can come up with this great story of a groundwater model that was made for Miami-Dade well field that predicted that travel times from a quarry to the well field would be many days or months. So they designed a dye trace, and they used enough dye to travel that long, days to months. And in fact, the water got to the well field in hours, and as a consequence, so did the dye. And the dye was promptly sent out to everybody's washers and turned their whites pink. So that's the name pink underwear test. So these processes are not subject to political borders. So what have I learned? I've learned that there really are such things as underwater or underground rivers. And those are just some pictures of caves throughout Florida. These things, the more we look, the more we find. We keep finding more caves, and the ones we thought that were fully explored keep getting longer and longer. The longest caves span tens of miles across the basin. Cave passages can vary greatly in size, even within a single system. The biggest caves are more than 200 feet across, and the smallest are too small to fit through. Big caves are slower flow, of course, and small caves have faster flow. And finally, caves carry loads of sediment and debris, and then along with it, contaminants and anything else that we put in the water. Caves carry a lot of water very quickly from upland recharge areas to springs. That's it's not exactly an underground river, but I think it's more productive to think of them that way than to think of them as non-existent. So how do we bring this to springs? Let's look at the ideal, or how many people sat in science class and listened to the phrase under ideal temperature and pressure. I was always the guy that asks, what happens when it's not ideal temperature and pressure? Well, on the left, I show the ideal condition, the diffuse flow condition, no such thing as springs. And on the right, this is closer to the real world, where springs are the end points, the discharges from cave systems that extend upwards into the recharge area, and the groundwater is flowing and converging into those caves and then out to the springs. So you can think of the caves, I like to think of them this way, as if we think of them as the underground rivers, then the water table would be like the topography. And essentially the water is flowing off the slopes from the recharge areas into the caves and then very, very quickly out to the spring. So when we think about travel times, it's not so much how far away the spring is from your potential point of contamination. It's better to think of it as how far away that potential point of contamination is to the closest cave that would convey water to the spring, because that's really closer to the control. So how do these caves get made? Lots of people study that. I could give the talks just on that, but to simplify it, essentially the limestone, the rock is soluble, rain is a little bit acidic. So as soon as it rains on top of soluble rock, you dissolve it, and that is what creates the pore space. Other scientists have shown that once you get this permeability system, we develop what are called feedback loops. So on the left side, we have the positive feedback, where dissolution causes increases in permeability. The increases in permeability through the rock cause more water to flow in those places. And the more water, of course, increases the dissolution, which increases the permeability, thus the positive feedback. And while that's occurring in those places, the places that are adjacent can receive decreased amounts of flow. And therefore, you get almost a negative feedback system where you can actually cause permeability to be lost. And then if we want to look for caves, I've spent a lot of time in my career talking with people about trying to develop the magic technology that we could scan the surface and find the caves. And if we could do that, then maybe we could better protect the aquifer. But researchers have shown, and these are ones that, of course, I ascribe to. Peter Huntoon was my advisor when I did my PhD. Some of the researchers point out that caves are more likely a consequence of the flow through the soluble rock than they are through faults or fractures that exist in the rock. And by that, basically what it means is that if we can walk the land surface and identify the recharge areas, where does the water get into the ground, and then identify the springs where the water comes out, the caves are likely to be oriented at pretty much as straight a shot as you can get that conveys the water from the places where it gets in to the places where it gets out. And if we put this together, I just kind of show you this little model that I put together to give you an idea, my idea of how caves evolve. So if we start with the Florida platform, imagine back when it first emerged from the sea and was exposed to rain, there were no caves. And as the rain fell on the rock, it exploited random variables in permeability, and you started to get some little tiny springs where the water was discharging, and on the upside you got these little tiny holes where the water could get in faster, and you start developing this dissolution fingering process. And these very early type of system might be an example of blue springs. As the caves develop, they grow, and the caves will likely grow a lot faster from the down gradient side. From the springs, they grow upward into the aquifer, while on the up gradient side, where you might have sinkholes and places where water's getting in, they're also expanding down into the flow field. Eventually they'll connect and you end up with a system like Wakulla Springs. And then if you play that forward long enough, So where the caves get really, really big and the velocities slow way down, and you end up with the caves becoming, instead of pathways for groundwater flow, essentially they become the storage. And that, I think, is closer to what you have in places like the Yucatan Peninsula of Mexico. So how do these, let's kind of play it out. How does the spring system evolve? Let's say we have the river, maybe like the St. Johns River, and springs along the river. Caves of different sizes connect to all of these springs, and the groundwater surface adapts to the presence of those caves, creating directing flow to the caves, which then convey the caves to the springs. The caves capture the groundwater from broad areas, from the recharge areas, and ultimately the vast majority of the flow goes to the springs. Very little of it gets past these cave systems and these spring sheds to diffusively flow to the river. And this is the result, is what we think of, or we define now, as a spring shed. So we have 3 spring sheds capturing water and delivering them to the spring, delivering that water to the springs. And in some places you can have some complicating factors, particularly where there's confinement, in that you can have surface water bodies that disappear completely. Disappearing streams are very common in Florida, and therefore you can have a spring shed like this, in case the middle one, that's taking water from its capture zone in the aquifer, plus a portion of the land surface that overlies an adjacent spring shed. So you can have these complicating features like this. So now if we take this concept of the spring shed and we map it out, in this case, what I've done, or my team and I did, is we took all of the groundwater levels from peninsular Florida and built these groundwater surface maps and then drew lines to show where the spring sheds are located. And this is where the water comes from for each of these springs. So this box is the spring shed for Rainbow Springs. This box over here is roughly the spring shed for Volusia Blue Springs, De Leon Springs, so on and so forth. So the water doesn't come from miles and miles, and doesn't come from the Appalachians. It doesn't come from the Great Lakes. It comes from essentially these localized areas. That's where the recharge comes from, and that's where they can become contaminated. And if we do this in high water and low water conditions, if I go back and forth, you can see that these are not fixed like watersheds. These boundaries aren't defined by topographic ridges, of course. They're defined by pressure in the aquifer. And by seeing that they can move, what we're really seeing is that they can be affected by things that we do to them. So they can be affected by drought, and they can also be affected by pumping. So as we take more water out of the aquifer, we can change the shape and the size of these spring sheds, which of course changes the amount of flow that goes to them. So where does the water come from, or where has it gone? The water that most of you drink, of course, comes from the springs. So when the wells pull water out of the ground, it's capturing water from its pathway that it would have taken naturally otherwise. And most of those pathways, of course, would have been to the springs. So I always used to laugh about the idea of spring water bottling, because if you turn on your tap in Florida, you're pretty much drinking spring water. Water pumped from the wells is captured from its natural flow to springs. Springs flows have diminished because we've mined the pressure that historically kept them flowing strong even through droughts. And as an example, I've got a couple of pictures of spouting wells. On the left from a well, a picture taken around 1948 outside of Orlando, and on the right, a spouting well also from the Orlando area in about 1911. So there used to be a very large amount of pressure in the confined portions of the aquifer, and that pressure is what pushed drove the spring flow and kept them constant even through droughts. That pressure, of course, has been diminished greatly because of our pumping. Where does the water come from? Spring water isn't as old as we'd like to believe. The springs are green because we're contaminating the groundwater. with our wastewater, with our fertilizer, with the things that we discard into the land surface, thinking that they never reach the springs. But in fact, groundwater flows much faster than than a lot of us think, and than we used to think was even possible. And of course, when that groundwater flows fast, it carries the contaminants with it. It comes from your backyard, metaphorically. So why are they important beyond their beauty and their ability to inspire? Springs are important because they are a measure of the aquifer's health, of how much water you have and how clean that water is. The way I like to think of it is they're your monitors. If you have strong, clean spring flows, those are the earmark of a healthy aquifer, one that can sustainably supply clean, fresh water forever, and one that is intelligently managed. So those having springs is a mark of those two realities. On the other hand, diminished and contaminated spring flows mark the beginning of the end of your water resource. So what must be done? In my opinion, we need to reject the myths about slow-moving ancient groundwater. And more you than the scientists, I think, the people here, is to look beyond your friends, the people that are probably here, that care deeply about springs, and try to build alliances with a broader group of Floridians who all share a common desire and a common need, which is to protect your water resource. What must be done? Substantially reduce and cap nutrient releases. Advanced wastewater treatment, as we've heard about lots today now. Other technologies like artificial wetlands, reduced use of fertilizer, both for homes and agriculture. Achieving the needed reductions will likely take all three of these and more. It's not going to be popular, and it certainly won't be cheap, but it's the only solution to your eutrophication problem. In terms of quantity, in my opinion, the only solution is to establish caps on groundwater consumption. Those caps need to be less than what you currently use. The springs don't care what you use the water for. And I think it's also important to start to embrace ideas like artificial recharge. So consider your footprints in terms of consumption when establishing policies, both personal and public. I like to throw out this little charts like this. You can find these online. More and more people are looking at how much water does it take to make the goods and services that we use every day. And it takes, according to these, it takes about 400 bottles of water to make 1 bottle of milk. But take heart, because if you switch to beer, you can save about 15,000 gallons a year for each glass every day. And with that, I'll say thank you, and also thank all of the different agencies and the people that I've worked with through the years that have helped me with this kind of work.
Thank you very much, Todd. We have a couple of questions in the Q&A. And let's see. The first one is, please explain what you mean by aquifer pressure.
So the aquifer pressure is, so imagine that if we drill a well and we lower a tape in the well and we measure the water level. And the unconfined portion of the aquifer, that we would think of that as the water table. And that would be like you could dig a hole and you encounter water as you go down. In the confined portion of the aquifer, in days gone by, in some cases we can still find it, but if you were to drill a hole through that confining layer, the water would have risen higher than the top of the aquifer. And that means it's under pressure. And in the case of those spouting wells, the pressure was so high that when you tapped into it, it shot out of the ground surface. And we, through historical times, Florida has had many flowing artesian wells. Unfortunately, we were not wise enough to even bother to cap those wells through the years, so they were just left to run and just drain to the surface. So that pressure is now very much gone. And in some cases, the water levels are so low that we're inducing saltwater intrusion into the aquifer instead.
Okay. Here's one from Rick Kilby. Todd, I remember hearing you say that Florida springs are or will become ephemeral. I'm probably pronouncing that wrong.
Ephemeral.
Thank you.
Yeah.
Systems that fluctuate according to large water events like tropical storms. Is this still true?
Yeah, I think that's what we're seeing now. We are getting into this phase where we think about water conservation when we're in a drought. But if we look at the historical record of spring flows, what is very compelling to me is that historically springs flowed almost the same discharge, whether it was in a drought or not, whether you were in a drought or not. And now what we see is the spring flows are going up and down. So we go into droughts, some springs stop flowing altogether, like Hornsby Springs on the Santa Fe River. And it's only when we have big, large rainfall events that those springs flow at all. So a spring that used to be perennial is becoming ephemeral, meaning it only flows when you have sufficient rainfall to drive it. And that's because in the case of Hornsby, the city of Gainesville's well field has captured almost all of the groundwater flow that would have otherwise gone to Hornsby Springs. And that, of course, is happening at Blue Springs. It's happening at all the springs. The water that we pull out is competing with, is capturing water from those spring sheds.
Okay, and the next question is, thank you. Why is warm Mineral Springs not 72 but 85 degrees?
So that's a good question. It's a little bit outside my wheelhouse. I've actually looked for opportunities to work at warm Mineral Springs, and haven't had one. But as I understand it, as I know, warm temperatures are associated with geothermal activity, meaning the temperature of the earth is warming it up. So those warm temperatures can be associated with, like out here where I live, they're associated with the heat from what used to be volcanoes, and hopefully won't be volcanoes again, right near my house. But in Florida, I think it's more likely, and at warm Mineral Springs, that you have very deep circulation through deeper portions of the aquifer. So as you go deeper into the earth, you get higher temperatures, and as that comes up, you get the higher temperature water.
Okay. Would it be correct to say that the pressure in artesian systems is ultimately from gravity working on water flowing down gradients?
Yeah, absolutely. So essentially, the reason those wells were pressurized is because the recharge was occurring in the mountainous areas of Florida. And I, say that of course in jest, but if we really think about Florida, you got to take what you can get. So the highlands are maybe 200 feet high, 200 feet of elevation. I think the highest point in Florida is around 350 feet elevation. So recharge, like in particular, if we think about what we call the interlocking karstic highlands. So the karstic areas a little north of you, say north of Wakulla, in Central Peninsula, there's lakes up there that are connected to the Floridan aquifer, and recharge that occurs up there is sitting at a higher elevation. And so that elevation is what it pushes down into the aquifer and the confined portion and then out, and that's what gives you the pressure.
Okay. So you were talking about the dye tracer test. Are those used in all springs, or was that a specific?
I would love it if dye tracing became the common tool for hydrogeologists in Florida, but it is not a very commonly used tool. So they have not been used in all springs, but they've been used in many springs in west, central, north, lots of different places.
Okay. And to build upon your education plus science plus press equals results, there's a saying in sales that nothing happens until something gets sold. And one could argue that in the environmental world, nothing happens until laws get passed. What have been the most successful ways that you've worked with government entities, both local and state? And with finite funding available, how do we make sure our springs get their fair share?
By far, the most successful equation that I believe in is in public education and public outreach. And that's because I agree completely. You have to have laws, which means you have to have public policy. But from my perspective, and I don't mean to be cynical, but public policy doesn't happen until you have public support. So if you don't have a voter base that is strong enough that wants to do it, then it's just not going to happen. So as an example, in Tallahassee, there was huge pushback from the city about advanced wastewater treatment because of the expense. And, that there's this tendency to want to vilify people, put it, these are bad people, good people on the bad side of the environment, good side. I tend to try not to play in that pool, but instead just look at it as cause and effect. And when I talk with, people at the city, they're like, look, this is going to cost a lot of money, and it's going to have to be pushed onto the ratepayers. And they just didn't feel like it was something that they could do politically. But ultimately, when we got through a bunch of public outreach campaigns, there was literally a poll taken, and it was a big event in Tallahassee. And it turned out that around 70% of the people were willing to pay more for their water if it meant increasing protections for Wakulla Springs. And I believe that was kind of a shocker to people that the public was willing to pay more for that. And so I think that the public education component cannot be overstated. On the flip side, at Silver Springs, that very document I showed, the dye tracing, hundreds of thousands of dollars spent on that study, and it went nowhere, in my opinion. And that's because it was a great study, and the results were dutifully put into a report, and the report was put on a shelf, and nobody ever paid attention to it. So the difference in Tallahassee was that at the time we were doing the dye tracing, we were also engaged in public outreach. We were doing public presentations, at least one a quarter, if not more than that. Some of those were getting hundreds of people would show up, and of course the newspaper and the TV and the radio. And I think it was that drove the thing, that drove the actions, probably more so even than the science. Of course, science was good too. I was happy to do that.
Okay, thank you. I think we have time for one more quick one. Developers are clear cutting and changing topography for gravitational sewer systems. How does changing natural topography affect springsheds in the aquifer?
So in lots of ways, you can create sources of recharge where there weren't. So if you breach the confining layer, you can open up the aquifer, number one, to recharge, but also to contamination. Now, in a watershed, of course, changing the topography can change the watershed divides, and that's not so much the case with springsheds. But I think that the key there is how you change recharge. So when you think about changing the topography, what comes to my mind is the vision of bulldozers, plowing everything over. But what less comes to mind, but it should come to mind more, I think, is what we do to the surface of the land. So if we convert grass, or if we convert natural setting to rooftops or to parking lots, then we change the distribution of recharge, and we can actually end up taking water away from the springs, the same as if we put a well in and pumped it out someplace else.
Thank you very much. And there was an attendee who was wondering if he could use the "What I Was Taught" slide, and I don't know if that's proprietary, but if that's okay with you.
You can have all those slides you'd like.
Okay, thank you. That's very generous. Thank you very much. And thank you for your questions, everyone. So next up,